Okay, so we're going to get into single area OSPF, specifically version 2, talk a little bit about version 3 as well. Primary difference there is just version 2 is for IPv4, version 3 is for IPv6. So this is going to be a broad strokes type of overview of the course or of OSPF. So we're going to be talking about how OSPF actually works. We're not really going to be looking at the actual configuration side. We've done that a little bit in our prior class, but I'll be doing some demonstrations of that as well, kind of going forward. So overall, again, get a general idea of kind of your features and your basics of OSPF. So OSPF is a link state routing protocol, so it's different from, say, a distance vector protocol, such as an older routing protocol like RIP, or Cisco's other routing protocol, EIGRP. So there's pros and cons for it. When we look at kind of the difference between OSPF and, say, RIP or EIGRP with our distance vector, link state, we can kind of think of it like, I know about, it knows, if we look at, say, a router, and we have a couple different routers that are kind of set up and they're connected, such as that. And we know about all the different interfaces that are set there as well. So we have, a G00 interface, a 01 interface, 00, 01. Link state for OSPF means that each specific interface and point-to-point is all being monitored on a state-by-state basis. So whether the actual interface is in an up or down state, and if it goes down, then links change. So if you want to think of link state as anything, kind of think of it like Google Maps, right? So you know exactly where to go at each point, where to turn. It plans out the best path that you have, and if there's a large amount of traffic, it plans out an alternate path. It already has, how long it's going to take for every single thing. So that's kind of link state. We know exactly where each point is. We know how long it's going to take, and we're constantly monitoring each of the points as well. That works pretty well. Now, the difference with distance vector is if we are looking at this exact same scenario and we have router 1, router 2, and router 3 here, distance vector basically kind of works like signposts. If router 1 needs to send traffic over to router 3, it doesn't actually know where that is, but we have to actually try and figure out where we're kind of going. One second. Sorry. So with distance vector, like I said, it's kind of like signposts. So router 1, router 2, and router 3, if router 1 needs to send traffic over to router 3 there, essentially what it will do is, unlike link state, where it doesn't know each specific interface and how far to actually go, the best it can do is what it will do though is it'll say, right, if I need to get over to router 3, I know who to send it to next. So I'll send it to router 2. I don't know how far away router 3 is. I don't know where it is, but I know I can send it to this next hop, and then router 2 knows where to forward it to next. So that's kind of the idea of what we look at between distance vector and link state. So works pretty well. There's pros and cons for each. Um, Distance vector is arguably a little less intensive in terms of resources that we have to utilize. Link state, however, is pretty heavily resource dependent, where it's constantly asking the router to utilize and send out updates and messages and broadcast messages or multicast messages. So, yeah. So general components that we look at when we're looking at OSPF. So OSPF runs off of a certain number of messages that we can actually send out. So we have hello messages, database description messages, link state request, link state update, and link state acknowledgement. They're actually all pretty self-explanatory in the general area. A hello packet just says, hey, I'm checking to see who is also running OSPF. And if I see someone that's running OSPF and inside of it, it has this, you're running in the same area, then they partner up and they form adjacencies. Database description happens after an adjacency is formed. Database description messages are where the routers are sharing their routing tables essentially out towards the other devices. So it says here's a general description of what I have. Kind of think of it as a summary of of the routes that I have. It's not everything super in depth, but it's a general summary. Link state request then comes back where it says a router comes out and says, hey, I don't actually have this route that you just sent in your database description. I'd like to request that you tell me more about that route. Can you send me that information? And then the other router will send out a link state update, which includes the information related to that. And then you get the link state acknowledgement that comes back from the original router that requested that information to say, hey, thanks, I got it. Now I can move on. So we have 3 different databases that typically occur in OSPF as well. So we have our adjacency database, our link state database, and our forwarding database. Really, if you wanted to think of them in easier terms, it's our neighbor table, our topology table, and our routing table. They're kind of synonymous when you're looking at them. So an adjacency database just determines who I'm directly connected to. So who is my neighbor in OSPF. So it's your physically directly connected links. So if we look at something, say like packet tracer, if I'm saying who are my directly connected neighbors in OSPF, if I hook up these routers right now, router 0 here, and let's say they were all configured with OSPF, its neighbors would be router 1 and router 2. Router 1's, so both router 1 and router 2 would exist in router 0's adjacency database or neighbor table. Router 1 is only directly connected to router 0, so the only router that would show up in its adjacency database is router 0. Vice versa, router 2 would only show router 0. So it only shows your directly connected neighbors. The link state database, or your topology table, lists information about all routers in the network. So every single router that exists. So this is where all routers would know about all other routers. So everyone should have, all routers should have an identical link state database. And then we also have our forwarding database, and this is just our routing table. So this is your standard typical routing table that you see for our devices. So you can see it by typing in show IP route. Now, the one thing that we've kind of mentioned prior that we should kind of be aware of is remember about administrative distance. So with static routes, our administrative distance was 1, so that means it's the best route. The lower number you have for your administrative distance, the better the router thinks the route is. OSPF has an administrative distance of 110. So if you have OSPF running and then you write a static route for the exact same route, your static route will overwrite the OSPF route. So just keep that in mind when you're kind of looking and working through that. So how OSPF works is it works based off of what's called Dijkstra's shortest path first algorithm, or the SPF algorithm. This works based off of cumulative cost, so where it will factor in how the best path actually is created, and then it will kind of move from there. Now, how it actually puts together the best path, well, let's I did say that we weren't going to do any configuration, but we can do a little bit here. So let's go ahead and kind of just do some basic configs, just to kind of see what it looks like in our routing table as well. So we'll say no. And so what I'm going to do is just set up our router. Oops, I'm already in config mode. We'll just set up our router real fast. So we'll go into G00. I'll just give it quick IP address, turn the interface on, and then we'll go into router OSPF. And so what I'm doing here is I'm advertising in OSPF the directly connected network, so all networks that I currently know and that are going to be activated about. So in this case, I'm setting up a very simple one, so the only network that I'm sharing here is just the 10 network. So we're going to go into our next router, so router 0 here, and we'll go into G00. And then we'll go into our G01 interface. We'll do the same thing. We'll give that a 5. And then we'll do router OSPF as well. And just to as a reminder, the number that comes after OSPF, that's just a process ID number. I can pick any number that I want between 1 and 65,000 and some change. So it doesn't matter what that number is. It's just locally significant. So that number doesn't have to match between the routers. And then so for this router, because it is physically touching 2 networks, we're going to tell it about both networks that it's physically touching. So it's the 000 and the 004 network. And we can see that we already got an adjacency that just popped, so that's good. And then final router that will come over and configure real fast. We'll go into G00. Oops. And remember with OSPF when you're adding in, when you're adding or advertising the routes, we use wildcard masks. So that was what you saw me type there just a second ago. We'll get into router OSPF, and we'll advertise the network that we are touching. And we should see neighbor adjacency form. So if we look at our routing table, we should see a link there that shows up. And remember, when we're working with this, we see the first number that you see in your routing table, so with that 110 right there, is the administrative distance. And then the next number that we see is our cost, or how far away we actually are from our router there. So that's what we're talking about with that cost, is essentially what is calculated based off of the SPF algorithm, or Dijkstra's algorithm. what it'll do is it'll calculate based off of bandwidth as the primary factor there for determining cost. So the faster the interface, the better. Now, the one problem with the SPF algorithm is it was at least in its default state, it was currently configured. It was made back in the 80s, I think. And so back then, you know, a 1 gigabit connection was no one had even heard of that. So 1 gig, they're like, yeah, that might exist, but it will never really get there. And then, you know, 10 gigs, 100 gigs, you know, type of connections, that wasn't even thought possible to be done. So so the problem with the shortest path first algorithm is that it doesn't know how to differentiate between, say, a 100 gig, a 10 gig, or say a 1 gig pipe. They all are calculated off and look the exact same to OSPF by default. We can change that, but that is something to kind of keep in mind. So in the kind of process of OSPF, how it kind of initially goes through, our routers will start off by going through what's known as the link state routing process. So these routing steps for each router are completed in this specific order, where it goes establishing neighbor adjacencies, exchanging link state advertisements, building a link state database, executing the SPF algorithm, and then choosing the best paths, and then those best routes get added into each router's routing table. So one cool thing about OSPF is we have an ability to make it a lot more scalable and a lot more efficient as well. And so we can use either single area OSPF or multi-area OSPF. So we've used single area OSPF already, but what we're going to look at doing is also using multi-area OSPF down the road. So single area OSPF means that all routers are a part of a same single area. So they're all in one area. Typically, it's area 0, which is known as our backbone area. Now, in multi-area OSPF, we have multiple different routers that are in different areas, but they all have to be touching the backbone area in one shape or in one way or another. Now this can be done physically, where you have one router that is physically touching another router. So I think I've got a slide here. So you can see in this case, router 2, it physically belongs to both area 0 and also area 51 there. So that is how we kind of factor in. Now the way it does this is we specify which network is going to be associated with which area. So that's what you kind of saw when in OSPF, when I was configuring this, when I was typing in the commands and I was adding in network 10.0.0.4 area 0, that's me assigning a given connected network, so directly connected network, to a specific area. So if I wanted to change, or if I added another network onto this, and I wanted it to be in a different area, I could call it, say, like area 10 at the end of it, and that works too. So there's options there. Now, why would we want to do, say, single area OSPF over multi-area OSPF? So there's a lot of different reasons, but you typically won't for smaller networks. More times than not, you'll typically do it for more larger scale organizations for multi-area OSPF. But the benefit for using multi-area OSPF is 3 primary things. It gives us a smaller routing table size, and that's good because the fewer routes that we have in our routing table, the faster our router can process those routes. We have reduced link state overhead, which is very good because OSPF is very, very chatty when it initially starts up. So there's a lot of memory requirements. There's a lot of messages that are being flooded out to all the different routers. So that can be a big thing to kind of cut down on. And then reduced frequency of SPF calculations as well is our third primary aspect there. And that again just means that it minimizes, if the network topo changes, this minimizes how much those messages get sent out and how much gets changed. So we also have OSPF version 3. OSPF version 3 is for IPv6. It works pretty much equivalent to OSPF version 2. A lot of what we do works very similar in how those things actually operate. I'll talk more about OSPF version 3 later, but it's basically configuration wise and how it functions. It's pretty much identical grand scheme of things. So getting into our packets, we're going to talk about the different types of messages that are actually being sent out. So we have hello messages, database description, link state requests, link state updates, and link state acknowledgements. So a hello packet is just my router discovering neighbors to help build adjacencies between them. The database description synchronizes the databases between the two sides. So it says, here's what I know, here's a brief summary of what I know. Link state request, as I already mentioned, says, hey, can I have specific records of, say, this route that I didn't have that you just shared with me. Link state update is when the other device shares those messages across, and then the acknowledgement is just saying, hey, thanks for sharing that. So link state updates are forwarded via OSPF routing updates. So it can contain a bunch of different types of LSAs, so link state advertisements. The primary ones that we kind of look at is kind of important to know what those messages are. So we have router LSAs is number 1, checks for database synchronization between routers, number 2, summary LSAs is 3 and 4, autonomous system external LSAs is number 5, multicast OSPF LSAs is number 6, defined for not so stubby areas is number 7, and external attributes LSA for border gateway patrols, BGPs, is for number 8. Pretty much what you're going to focus on for a lot of these is router LSAs, check for summary databases, and summary LSAs, and then also autonomous system and multicast. We don't typically see too much with 7 and 8, grand scheme of things. Essentially what these do is this is just a flag that says this is the type of information that's going to be contained in the link state update message that's being sent back and forth. So when most routers, after they've sent out their updates or sent out their hello messages, you'll see summary LSAs, so type 3 or type 4, that are actually being sent back and forth between between neighbors. So a type 1 packet, this is kind of our initial hello message that's being sent out. So in our hello message, there's a lot of information that's actually being contained and being hosted, and so specifically the information that we care about is router ID and area ID. And we'll also see information such as the network mask, hello interval, dead interval, and then what we think the designated router and backup designated router are as well. Now, I'll get to those in just a sec, but the things that have to typically match in order for our routers to actually send traffic back and forth or for a neighbor adjacency to occur is area ID must match, hello and dead interval must match, and then network must match as well. So those 4 things have to match in order for our routers to establish adjacencies. So again, area ID just talks about area 0 or whatever area that you're setting up. Network mask is what our directly connected network actually is. And then hello and dead interval are how frequently we're sending out these hello packets. So this is basically a keep alive message. So it says, hey, how frequently should I check to see if the other connection is still up and operational? And then the dead interval is if I don't see a hello interval or hello message within a certain period of time, I'll consider this link dead, and then we have to go through the SPF algorithm again to figure out the next best path if we have an alternative path. Designated router and backup designated router are important. This gets us into who is actually sending out update messages. So in order to cut down on the mass amount of all devices having to send out their routing tables and make decisions, and all devices having to calculate the SPF algorithm, we can set up a primary router to do all of those calculations and make all that. And then we can set up a backup router in case the primary router goes down. So that's what we call a designated router and a backup designated router. For the most part, you don't typically have to deal with this too frequently in smaller scale networks. It's not that important. Your routers will actually have, there's a built-in process for it to automatically be able to do that itself, and determine what the designated router and backup designated router are. But in larger scale networks or medium scale networks, you want to typically make those things or make those determinations yourself. So OSPF operations. So we have our 7 states that we typically see: down, init, two-way, xstart, exchange, loading, and full. So this is the full process for how what our router actually takes in order to get to basically a fully functioning OSPF message back and forth between everything. It's pretty quick, like you saw in the demonstration that I just did really quickly, setting up OSPF for a couple of systems. It took maybe a couple seconds in order for it to process and go up. But each router has to go through all these steps. So a down state just means that nothing's working. It's down. The port's down. Init state is where our hello packets are first actually being sent out. And if the hello packets are actually being accepted, then we move into a two-way state, which is where both routers are going to be sharing information back and forth, and starting to determine who's going to be the designated router and backup designated router. Then it moves into the xstart state, where our routers decide which router will initiate and actually be the one that's making the sending out the database description packet exchange and messages. Then it moves into the exchange state, where routers are actually going to be sharing their routing tables and routing information. Then it moves to the loading state. This is where the SPF algorithm is starting to be actually calculated. And then it moves to the full state, where our databases or linked state databases are synchronized and our routes are properly added into our routing table. So some things that are important to know: those hello messages that are being sent out back and forth between our devices are being sent based off of multicast messages. So it uses 224.0.0.5 and 0.0.6 are the two primary routes that we see, or not routes, but IP addresses that we utilize. Again, the router ID, how that's calculated out is it's based off an IPv4 address. So it will go off of an election process, or in order to determine its router ID, it will start by trying to go, okay, do I have one manually set? And if the answer is no, then it goes to its next best option, which is, okay, well, do I have an IP address set on a loopback interface, so like a testing interface? Now it will check that because a loopback interface starts in an up and up state and won't typically actually go down unless you manually turn it off. So it's the next best thing besides manually setting it. If that's not set, then the next thing it will do is it will just check and pick the highest up and up interface, the highest IP address on an up and up interface specifically, and that IP address becomes its router ID. So if we take a look at, say, like router 2 here, where I looked at this, I can say show IP OSPF, and we can see my router ID is 10006. Well, if you look at what I have in my running configuration, the only IP address I have is 10006 on the gigabit 00 interface. So because I didn't manually set a router ID, because there's no IP address set on a loopback, it pulled the highest existing IP address on an up and up interface and turned that into its router ID, and that was 10006. So that's how it determines it. So the router ID is the way it works, though, is that your router ID is always going to be based off of whoever becomes the designated router. That device gets the way the designated router is determined is the router that has the highest IP address. So if it has the lower the IP address, the less likely it's going to be a designated router. So we kind of went through that as well. So one thing to know, again, with our synchronization of databases, it happens every 30 minutes, or anytime that there's a change in the network is found in the linked state database. So the primary idea for having a designated router is if we have a lot of different adjacencies, it limits the amount of flooding of the linked state advertisement messages that are actually being sent out. So that's the primary reason that we have it. It also allows a single router to make the determination and changes when a change occurs in the network. So the one extra thing to last thing to leave you off with there is that so we mentioned designated router and we mentioned backup designated router. If we have more routers in our network, they're called druthers, or DR others. So the designated router makes the primary changes, backup designated router is the next important one, and then all other routers are the druthers. Now, the one thing to note too in the election process is that if the designated router goes down, the backup designated router immediately takes the place of the designated router, and then the other routers, the druthers, will hold a new election process to determine who becomes the new backup designated router. Now, when the designated router, the old one that went down, comes back online, the downside to this is that by default, it will not take back the designated router position. So typically we have to start some form of a redo in the OSPF process in order to do it. Not that big of a deal, but is something that we have to keep in mind. Alright, that's all I have for you for this initial chapter. Hopefully it was helpful, and I will have more videos coming soon.